Hello class. Today we are going to do Unit 7, Lesson number 6, so the last lesson. It will be 7.6, Solving Quadratic Trig Equations. So before we go on to solving quadratic trig equations, let's just review how we'd solve quadratic polynomial equations. So that would be of the form ax squared plus bx plus c, where we find two numbers to multiply to a times c and add to b. Plug those numbers. If it's a simple trinomial, we plug those numbers right into the brackets, and if it's complex trinomial, we use decomposition and factoring by grouping. So today what may happen is that we may have a situation that looks like this. So a sine squared x plus b sine x plus c. So this is quadratic based on that degree of 2, and it's quadratic trig equation because instead of having, for example, that x here that's getting squared and the x here, you now have sine x getting squared and the sine x here. So it's all the same format. You just have the trig function in for the x here. Also, let's remember difference of squares. You may have to do that in the homework. So you've got an example of that in trig form would be cos squared x minus tan squared x. All right, so remember you find the square root of the first term, square root of the last term, and then you put them in brackets. So you write it as a plus b and a minus b. Okay, so just a little review. Here we've got a complex trinomial, so we're going to look for two numbers that multiply to negative 12 and add to 4. That is 6 and negative 2. So we have 3x squared plus 6x minus 2x minus 4. We're going to do our factoring by grouping, factor out a 3x from the first two, and a negative 2 from the last two. We know we've done something right when the x plus 2's are the same, so we factor that out, and then we're left with the last factor of 3x minus 2. When you're factoring a difference of squares, so remember you square root the first term, which would be 6x, and you square root the last term, which would be 7y, and then you plug it into two brackets, one with a plus, one with a minus. So 6x plus 7y, 6x minus 7y. Something else to remember that you may have to use when you cannot factor using these methods here, when you cannot easily find those two numbers, then you're going to use the quadratic formula. So remember that's x equals negative b plus or minus square root of b squared minus 4ac all over 2a. All right, so what are the steps for solving a quadratic trig equation? So really, the only two extra steps that are new are going to be steps 1, 2, and 3, really. Okay, so the new step here is that, again, whenever you solve an equation, you always have to bring all terms to one side of the equation and set one side equal to 0. And we always do that when, remember with polynomials, we did that with a degree of 2 or more. So you're going to do the same thing with a quadratic trig equation. Okay, so you're still going to bring all the terms over, set one side equal to 0, and then of course your next step is to factor. Okay. And once you have factored, your next step is to set each factor equal to 0 and solve. Okay. So once you set each factor equal to 0, what happens is you're going to be left with linear functions. Okay, so for example here, once you factor, you're going to get a linear function times another linear trig function. So after that, you can treat and solve the factors by solving the way we did in 7.5. Okay. So after that, you just isolate the trig function. Okay. Use special triangles or the inverse function to find the related acute angle. You use the cast rule. Again, you can interchange these two if you'd like. And then you determine the two principal angles. Keep in mind, if you're working with special cases, for example, where you're trying to solve for when something's equal to 1, negative 1, or 0, a quick way to come up with those x values is follow this arrow here. So for example, if you have cos x equals 0, I usually think of 0, okay, well that's the zeros of the cos function. So I usually draw a sketch for myself at the side, and then I tell myself, okay, where does cos cross, or where does cos have a y value of 0? And that's here and here. Okay, so that means the solutions would be here, x equals pi over 2 and 3 pi over 2. If, for example, you get something like sine x equals 1, right? So 1 and -1 are the max and min values of the trig function sine and cos. So for sine x equals 1, I again draw my sine function, and I see, okay, well, that's going to equal 1 at the x coordinate pi over 2. So if you ever have a trig function equal to these ones here in terms of sine and cos, the best bet for you is to draw a little sketch of the graph. And keep in mind that if k does not equal 1, then you have to add the period to each of the angles found in step 7. So that still applies. Alright, so let's jump right into it. It says sine squared x minus sine x equals 2. So the first thing we want to do is we want to bring that 2 over to the other side. Okay. So with linear, you want to isolate the trig ratio, but with quadratic, that means you have two pieces that have sine x in it, so that's why you want to bring everything over. So we bring that over, and if you want, so if this kind of looks ugly to you, you can come up here and you can say, you know, let some other letter y equal sine x. And then you can rewrite the expression as y squared minus y minus 2, if that visually helps you. Okay, if you can already see the quadratic form there, that's fine. So we see that this looks like a simple trinomial. So I'm going to look for two numbers that multiply to -2 and add to -1. And that's -2 and 1. So because it's a simple trinomial, I can just plug those right in as the factors. Now notice we're used to writing x minus 2, x plus 1. But that's when it's polynomial, so that's when the variable is just x. Remember, our main function here is sine x. So if we're gonna put it into factored form the way we would normally, now we have to put sine x minus 2 as one factor, and then sine x plus 1 as another. And of course, whenever you expand something out, when you do FOIL, you should get the previous line back. Alright, so now we've got these two factors, and now let's work with them. So we're going to work with the first factor. So sine x minus 2. So we have to set each factor equal to 0 to solve for x. So now that we're here, we're going to bring the -2 to the other side. So we get sine x equals 2. Alright, so right away, when you see sine x or cos x equal to a number greater than 1 or less than -1, you know it can't exist. So this actually cannot be solved. Okay, so even if you try to go into your calculator and you try to calculate beta, you're going to get an error symbol. Okay, and that's because x does not exist for any y values that go greater than 1 or less than -1, right? Because the range is between 1 and -1. So this one has no solutions. We're very excited because that's less work for us. Alright, part 2 is sine x plus 1 equals 0. Alright, so now here we have to isolate, because notice here now we have linear functions, right? So with linear trig functions, you want to isolate the ratio. The trig ratio, or the trig function. So we're going to bring the 1 over, so it's sine x equals -1. Okay. Now for something like this, remember I told you with values like -1, 1, and 0, I just want you to think of your parent function. Okay, so again, this is another easier one if we think of our parent function down here. So you can do a little sketch. Okay. And you should be asking yourself, where does sine x equal -1. So a y value of -1 would be right here. So that's at an x value of 3 pi over 2. Okay, so we know over this interval, 0 to 2 pi, the only time sine equals -1 is here. Okay, so the solution here is x equals 3 pi over 2. So, based on all of this, okay, so no solutions here, right? No solutions here, and then we have just one there. So the only solution for this equation is x equals 3 pi over 2. So this one was really quick. Okay, they aren't all going to be that quick, as you're going to see as we move through other examples. Okay, let's try the next one. It says 2 sine squared x minus 3 sine x plus 1 equals 0. We are happy here because all terms are already on one side of the equation. One side's already 0. So right away, we should be seeing that this is like a complex trinomial. So again, if you want, for here, if you want, you can write this as 2y squared minus 3y plus 1 equals 0. And then later, obviously, you would sub back in the y equals sine x. Okay, so remember, if you substitute it in to make it look better, at the end you have to put it back in. Okay. Okay, so two numbers that multiply to 2 times 1, so times 2, and add to -3. That will give us -2 and 1. So because it's a complex trinomial, we have to do decomposition. So 2 sine squared x minus 2 sine x minus sine x plus 1 equals 0. And now we're going to do factoring by grouping. Okay, so out of the first two terms, we can take out a 2 sine x. When you take that out, then you're left with 1 sine x left, right? Because sine x times sine x would give you sine squared x. And then minus 1. From the last two terms, we can take out a common factor of -1. And then we're left with sine x minus 1. Again, we are happy because the two brackets are the same. So our final factored form is sine x minus 1 and 2 sine x minus 1. Alright, so again we have to break up the factors and deal with each one separately. So let's start with part 1. We're going to set sine x minus 1 equal to 0. Okay. Then we have to isolate the function, so we're going to bring the -1 to the other side and it's going to become +1. So again, this is one of those max y values. So just think of your sketch, go to the side, draw a little sketch if you need to, and we can see that the sine function equals 1 at the x value of pi over 2. And there we go. So we get x equals pi over 2. So that's the only root for this factor. Alright, the next one will involve more work. So here we're going to say 2 sine x minus 1 has to equal 0. And again, you want to isolate for sine x. So we're going to bring the -1 over. So we get 2 sine x equals 1. And then we are going to divide both sides by 2. Okay. So what we get left with is sine x equals 1 over 2. Alright, so obviously a number like 1 over 2, we can't easily see that on our table of values or in a graph here. So to find that, we're going to have to go through the same process we went through in our previous lessons and previous units even. So your first thing you're going to do is you're going to analyze the sign of the ratio. So sine x is positive in quadrants 1 and 2. So draw your sketch. Okay, so we've got x1 here, x2 here. Next step is you want to find beta. What's nice is that this ratio is already positive, so you don't have to worry about remembering that rule. So sine beta equals +1/2. And here, you should be thinking, okay, 1 over 2, that can happen in the special triangle here. So beta is pi over 6. So that means x1 is equal to beta, which is just pi over 6. Okay, so that's the blue one. And x2 is equal to pi minus beta, so pi minus pi over 6, which is 5 pi over 6. So remember, if you need to highlight all your answers, there are a lot, so highlight your answers or box them just like I did here. So there are 3 solutions for this whole equation. That's pi over 6, 5 pi over 6, and pi over 2. So all 3, when subbed in, would make this side equal to 0. Okay, so you have to list those as all 3 of the solutions. Okay? And it doesn't matter which order you write them in, but usually we write them from smallest to largest, but it doesn't matter to me. Okay, let's try another. It says, use a trig identity to create a quadratic equation. Then solve the equation for x in the interval 0 to 2 pi. So look at the equation we're given. We're given 2 secant squared x minus 3 plus tan x equals 0. So right now this isn't good for us to work with because when you're working with this, a quadratic trig equation, as you can see in these scenarios, you're going to want to have the same ratio involved. So you can't have like a cosquared here and then a tan x here. That's not going to be helpful. So we have to think of how we can rewrite one of these parts using a trig identity. So right now the more complicated part looks like the secant squared x. So based on a Pythagorean identity, okay, so have your formula sheet out when doing the homework, we can write secant squared x as 1 plus tan squared x. And I can already tell that that's going to be helpful to us because then we've got the quadratic term here and it matches with the other linear term right here. So we do 2 times, and then remember to distribute that 2 into both pieces. Okay. So then you're left with 2 plus 2 tan squared x minus 3 plus tan x equals 0. So let's rearrange this, collect like terms, and put it in the nice quadratic form. And so you get 2 tan squared x plus tan x minus 1 equals 0. Remember that equals 0 should be maintained throughout all the steps because that shows someone you are solving an equation. Alright, so here we have a complex trinomial. Okay. So we're looking for 2 numbers that multiply to -2 and add to +1. Okay, so those are going to be 2 and -1. Alright, we are going to use decomposition. So I rewrote the middle term of +1 tan x as 2 tan x minus tan x. Then you're going to do your factoring by grouping. So take out a GCF of 2 tan x and a GCF of -1 from the second. And your final factored form should be tan x plus 1 times 2 tan x minus 1 equals 0. Alright, so let's work with the first one. Okay, notice this is going to be a lot of space because we have to do a lot of work for the first factor and the second factor. So the first factor is tan x plus 1 equal to 0. So we're going to bring the 1 over, so it becomes negative. Now keep in mind, with tan x, when you work with -1 and 1 or 0, remember tan x's graph, if you can kind of keep that in mind, but usually students sometimes forget that. So when you have tan x equals -1 or 1, you can go ahead and work with it because that actually relates to a special triangle. So when you work with a special triangle with pi over 4, remember it has opposite and adjacent sides of 1 and 1. So again, your first step will be tan x is negative in quadrant 2 and quadrant 4 based on Castro rule. So you're going to do your drawing. Okay, so there's x1, and in purple we've got x2. Now we want to find beta. Like I said, so I remembered that tan x equals +1. So tan beta equals 1. Remember, you ignore the sign when solving for beta. That's when beta equals pi over 4. Okay, so that was from our special triangle. Okay. 1, 1, and root 2. Okay. And like I said, pi over 4 is inside. All right, so now that we know it's pi over 4, let's solve for x1 and x2. So x1 is pi minus pi over 4, so 3 pi over 4. And then x2 is 2 pi minus pi over 4, which gives us 7 pi over 4. So for this first factor, these are the two roots. So if I plug those in, this would be 0, so then this times this would be 0, and that would satisfy the equation. So now we're going to work with the second factor. Okay, so now we're going to work with part 2. Okay. All right, so that is 2 tan x minus 1 equal to 0. Again, we are going to isolate for the tan x. So we're going to bring that guy over. Okay, so 2 tan x equals 1. And then you're going to divide both sides by 2, so we get tan x equals 1/2. All right, so start the process. Ask yourself, where is tan x positive? Okay, so that's in quadrants 1 and 3. You're going to draw your diagram. So there's quadrant 1, quadrant 3. Notice I labeled this x3 and x4. I just did that because I've already called those ones x1 and x2. So these are two new expressions, x3 and x4. It's okay if you start a new factor and call those x1 and x2 as well. That's fine. But just to remind yourself that you already have two before. All right, so let's find our beta. Okay. So our beta value is going to be found by doing tan beta equals 1 over 2. Okay. Unfortunately, even though 1 over 2 can sometimes work for sine and cos in a special triangle, it actually doesn't work for tan. So nowhere does opposite and adjacent of a side in a special triangle become 1 over 2. Okay. So for this one, you're going to have to do beta equals tan inverse of 1/2. Okay. And you are going to get that beta is approximately equal to 0.46 rads. Okay, so always round to 2 decimal places for this. All right, so x3 lands in quadrant 1, so we know x3 is just equal to beta. So x3 is 0.46. X4 here lands in quadrant 3, so we're going to do pi plus beta. So that's 3.14 plus 0.46. And that gives us about 3.6. So notice that we have 4 solutions here. 2 of them are in their pi form and 2 of them are in their decimal form. And that's okay. That just shows these 2 were able to be solved using special triangles and these 2 are not. So the solutions are, here we have 4 solutions, 3 pi over 4, 7 pi over 6, 0.46, and 3.6. Okay. And remember, we've been very lucky with all these questions. The k values have been equal to 1 in all the factors. These can get very lengthy. For example, when you break it down to 2 factors, and then you have a k value that's 2. So for example, if I had a k value of 2 in here, then I would have to take these 2 values and I'd have to keep adding the period to them. Okay. All right, and let's try the last example. So we have 3x squared plus 3 times cos 2x equals 2. So at first glance, we're unsure because this doesn't look like a quadratic trig equation. So I want you to think of the double angle formula for cos 2x. Remember, it has 3 versions. Which version, if I subbed it in, would turn this to a quadratic equation that has the same trig function of sine? Okay. And that would be the version 1 minus 2 sine squared x. Okay. So the double angle formula is 1 minus 2 sine squared x. And now we've made it quadratic, all in the same form. All right, now I want you to distribute the 3 into both parts. So into the 1 and the negative 2 sine squared x. So we get 3 sine x plus 3 minus 6 sine squared x minus 2 equals 0. And when we put it in our nice form, right, we always want it in the form that we're used to, right, ax squared plus bx plus c equals 0. But it's trig, so we have negative 6 sine squared x plus 3 sine x plus 1 equals 0. So we can see that this is a complex trinomial. However, when we try to solve it normally, we get, we can't find two numbers that multiply to negative 6 and add to 3. So that means we have to try the quadratic formula to see if there are roots, or maybe there aren't any at all. So a is negative 6, b is 3, and c is 1. Now keep in mind, when we solve an equation like this, okay, using quadratic formula, we write x equals, and then negative b plus or minus, right, and then dot, dot, dot. And that's because this part, okay, has to match with this part here, right? Now notice, this is what's tricky that students always forget. We don't have just x anymore. We have sine squared x, okay, as our letter, okay, and sine x here as our function. So when you do the quadratic formula, sorry about that. Fix this. Okay, so when you do the quadratic formula, instead of writing x equals, you're going to write sine x equals. Okay, if you don't do this, you're going to end your question very, very early. Okay, so it's not just x equals like this was. That made sense for that scenario of a polynomial. Now you've got sine x equals, and then the rest of the formula stays the same. So we plug it in, and when you filter through, make sure you're keeping the two negatives there, make a positive. Okay, so you should get negative 3 plus or minus square root of 3 squared minus 4 times negative 6 times times positive 1 divided by 2 times negative 6. So that should bring you to negative 3 plus or minus root 33 over negative 12. So what does the first scenario look like? The first scenario is going to be, again, writing sine x is equal to, and then I want you to work with the positive version first. So negative 3 plus root 33 over negative 12. Go ahead and enter that into your calculator. And you should get negative 0.23, okay, rounded. So round to 2 decimal places. Notice that this is a scenario that we can solve. It's not a nice, right, we're used to having like a fractional form ratio, but that doesn't matter. We can have a form that's in decimal form. So let's go ahead and solve it. Go through your same steps. Okay, so sine x is negative in quadrants 3 and 4. So go ahead, draw x1 in quadrant 3, x2 in quadrant 4. Now we have to find beta. So we say sine beta equals positive, remember ignore the sign of the original, positive 0.23. Beta equals sine inverse of 0.23. Okay? And this is an interesting scenario. We got that beta is actually equal to 0.3 rads. Okay? So I know it seems weird. Beta was equal to what the ratio was in positive decimal form. Okay, that can happen. All right, so x1 is going to be found by doing pi plus beta, so 3.14 plus 0.23. So we get our first value of 3.37 rads. And our second one is going to be found by doing 2 pi minus beta. So 6.28, right, is the decimal form of 2 pi, minus 0.23, and that gives us about 6.05. So those are the two roots that match with this expression here. All right, now let's work with the negative version before the root symbol in the quadratic formula. So that is sine x equals negative 3 minus root 33 over negative 12. So put that into your calculator, and this side should simplify to about positive 0.73. So you have sine x equals 0.73 rad. All right, you know the drill. Analyze. Sine x is positive in quadrants 1 and 2. Okay. So we draw that in. So like I said here, you can label these x3 and x4 since you've already dealt with x1 and 2 here. Or if you want, you can start all fresh and call this x1, x2 for this scenario, okay? It does not matter to me, whatever works for you, right? All right, so sine beta is equal to positive 0.73. Beta equals to sine inverse of 0.73, and that should be about 0.82 rads. So that means, let's work with our first value here, that x1 is just going to be equal to beta, so 0.82. And x2 is going to be equal to pi minus beta, so 3.14 minus 0.82, and that is a value of 2.32 rads. All right, so those are our 4 answers. So these were the 2 that answered to this part, and these are the 2 that answered to this part here. Okay, so remember that the sine x is placed right here for quadratic formula. So altogether, our final answer is that the solutions are x equals 0.82, 2.32, 3.37, and 6.05 rads. And again, none of these scenarios, so the sine x here had a k value of 1, so with none of them we have to go back and add the period. But like I said, if that does happen, you could have up to 8 different solutions. So it could involve a lot of work at some times. All right, I hope everyone enjoyed solving quadratic trig equations. Make sure you practice the homework and let me know if you have any questions whatsoever. All right, good luck.